This is GeeklyEDU Math, and we welcome you again to our channel. Today's video is about one really useful coordinate system, cylindrical coordinates. Together, we are going to solve a transformation problem, and you will understand the geometry of this peculiar system. In our first video about curvilinear coordinates, we saw the polar coordinates, and you can also learn about the cylindrical coordinates, and if you haven't seen those videos, here is the link for you. Cylindrical coordinates can be used to solve tons of problems. Among those, you can explain the mechanics of the water or a fluid on a pipe, or even get the address of a song or a picture on a hard disk drive called cylinder head sector. Cylindrical coordinates are a generalization of the polar coordinates of the plane, based on extending them to the space parallel to the z-axis, perpendicular to the xy plane. The radial coordinate, ρ, is the distance of a point to the z-axis. The azimuth coordinate, θ, is the angle that the projection of the position vector on the xy plane forms with the x-axis, just like the angle in the polar system. And the vertical coordinate, z, is the distance of the xy plane. Now, we will have to use the trigonometric identities we learned before in the video Trigonometric Functions to find out the relationship between Cartesian and cylindrical coordinates. We can see that the components in x and y depend on the θ angle, so we'll start with the component in x. In this one, the hypotenuse is ρ, and therefore x is equal to phi cosine of θ, and y is ρ sine of θ. The z component is the same in both coordinate systems, since it is the height of the point in the three-dimension system. To find how big is the vector ρ, we will use the Pythagorean theorem, and so the norm of the vector ρ is the root of the sum of its components squared. In this case, the components of ρ are x, y, and z. To know the component θ, we will use the trigonometric relations, and we can use sine or cosine. Sine of θ is equal to the opposite cathetus divided by the hypotenuse ρ. And again, the z component is the same in both coordinate systems. Now let's solve an example together. We want to know a point that we have in the cylindrical plane, 6, pi divided by 6, 3, and we want to know this same point in Cartesian coordinates. To find the x component, we are going to use the formula that we got before. X is equal to ρ cosine of θ, and by substituting the values of this point, 6, pi divided by 6, 3, we have x is equal to 6 multiplying the cosine of pi divided by 6. This value you can get it in our previous video of trigonometric identities and trigonometric functions, and we have that x is equal to c multiplying the root of 3 divided by 2. So our final number is x equal to 5.2. Now, to get the y component, we are going to use the equation y equal to ρ sine of θ. We are going to substitute again the values. Now, y is equal to 6 multiplying the sine of pi divided by 6, and sine of pi divided by 6 is 1/2, so y is equal to 3. And finally, the z component is the same because in both systems, z is equal to z and both are the height. and z is equal to 3. And finally, we have our three numbers, and the drive of Cartesian coordinates x, y, z is 5.2, 3, 3. Now is your turn to solve an exercise. Consider a particle constrained to move on the surface of this cylinder. After 5 seconds, this particle moves to a position in the coordinate system x, y, and z equal to 8, 3, 2. What is the distance from the origin of the cylinder to this point and the angle that the projection of the position vector on the xy plane forms with the x-axis? Solve this problem and tell us in the comments below the answer.
Don't forget to subscribe and check out other videos for related topics.